So we have one main beam and those composite beams. So you see many of those beams are okay, they are very low stressed, but why these beams are more, we can right click and see generally if the design is correct or not. So the section is the same. The reason is, if you remember, we designed these wall post elements in the way that they are not taking axial load. That means those beams are being supported by middle columns, but these side beams are not being supported by wall posts. That's why they have higher stress. So let's check the detail and see what we have here. So here the whole length of the element is 16 meters, which is correct. That's the length from corner column, which is this column, to the middle column. So this is about 16 meter. Then we're coming here and those are the loads we have. So the moment is 65 kilonewton meter, which is not a big moment. Generally that 310 UB should be okay for that. So I'm coming here and I see the ratio is 0.9. So what do we have here? L factor is 0.365 for major and minor. I need to check here that if this element has release at the end, then this factor is not correct for major. We need to consider the whole length. For minor, this factor is correct because you have the struts and braces, so it's literally divided to 3 segments in terms of effective length. So 0.375 is roughly okay. So one of them could be longer than the other. So SAP taking the worst one, so you may have 0.32, 0.34 and 0.37. SAP designed it based on 0.37, which is the worst case scenario. And then we're coming here and we see what's the calculation for biaxial, and also what are the other factors here, is the section is compact or not, and how much they help to increase the capacity. So here the moment is 65 kilonewton meter. This is the maximum capacity of the moment when you have very small effective lengths. And then when we're coming here, this is the capacity due to actual effective lengths we have. So when we're coming to major moments, you can see here the other factors, and B is actually the capacity we have for moments considering the effective length. So this 75, that's why it's very close to 1. And you see the axial load itself is not too much critical. You have a big axial load capacity, so moment here is critical. If I close these, you can see these ratios here, that for moment it's 0.944, for axial is just 0.008. That means axial is not taking too much, the majority coming here. So in a glance here you can see the ratios, how they calculated. So this number is these 3 together. You see this is 0, but this is the major one currently. So when you're coming up, you see these numbers are different. So still axial is not too much, mainly it's for bending. So what I need to do, I need to cancel this. I need to back to undeformed shape, and I need to right click on this and see, do we have any end release or not? We do have end release. If we have end release, that shouldn't be taken into account for major bending. That means for major bending, actually the length is 1. So I'm coming here. As I said, I can back to the design and right click and go to override, or I can come here, just select this element and then view revise override and see what needs to be changed. So here we have unbraced length ratio major, that should be something around 0.98. This is because of the rigid zones we have at the end. We can calculate it accurately, but actually it doesn't change the result too much, 0.96, 0.98 or even 1. So you can logically put a number here based on your experience. And then unbraced length minor, we have purlins here to support roof cladding, so they are as lateral support. There are cold form sections like C or Z. How we can consider an element as a lateral support for column or for beam? That element should be able to support 2% of the axial force of that element. If that lateral element can do this, then we can consider it as a lateral support. So based on our experience, we know that it can happen for this size of a structure. So we have 1.2 meters space between purlins. The whole length of the element is 16 meter, so it's coming something around 0.08, a little bit less, but it's really in this scale it doesn't matter what if you put 0.1 or 0.08. And then on brace length ratio for lateral bracing and buckling. So here again, this is in Australian standard is used for bending calculation, so I put this one here as well, and then okay, I just select this one because the rest of elements are designed. I didn't change anything, I want to save the time, so I just use this. Now you see the color is blue. So if I come here to PMM ratio and value, I can see it's just 0.36. so if I back to this, come to the details, I see when I change this lateral bracing ratio, just bear in mind which one doing what. So when you update your effective length, that's good for buckling. For bending moment, you need to consider your major bending and lateral bracing length, which is LTB. Now we change this L factor to 0.08. What is increasing the bending capacity is lateral bracing, LTB here. So if I come here, I see MB increase from 75 kilonewton meter to 201 kilonewton meter. It still is not full capacity. Can you see here? It's not MS, but it's pretty good. Now the ratio is smaller. So this is for roof beam. Now you need to check the deflection. So because you don't have any point here, you can't change the deflection. So if I come here and say I want to see this one in, for example, comp SG2, and press apply. Okay, now the extrude view can be seen. Now I'm clear what's happening here. When I'm on deform shape, I cannot see that, but when I'm in deform shape, I can. The reason is there is an option here in general option for show analysis model. If it's ticked, I cannot see the extrude view in on deform shape. I need to untick this one and keep the extrude here and apply. Now we can see this in both deform shape and on deform shape. So if I press apply here again, I can see that. So that was the reason. If I zoom here, you see the orientation of column is correct. So this is what I tried to show you at that time. So just to make it more clear for you, I need to back here and back to the standard, apply. Now you can see this. So here you have joints. If you can pick up these joints, probably you can see the displacement. But if you don't see the displacement, the easiest way is, as I showed you, just go to the moment. So you can come to the same combination you want to see. Come SG2 and say moment 3.3 for example. And then here, if you right click, here you can see the deflection. I am after relative, so this is correct because this is the whole beam. So the maximum displacement I have is in meter. Let's back to Newton and millimeter. The maximum is about 17 millimeter. So I need to check this ratio and see if it's okay or not. If I go to another element like this, because we have support at both sides, so this element is smaller, you can see the displacement is very small, is just 3 millimeter. So this is the total deflection of this beam. So 3 millimeter is very reasonable and a small number, so I don't have any issue with that. So the only thing remaining I will need to check with you is these composite beams. Let's have a look at those and see what do we have here. So you see the deflection of this beam is 7 millimeter, and the moment is not very big, is about 5 kilonewton meter. If I back to kilonewton meter unit, you see it's just 5 kilonewton meter. So this is not realistic, but is that realistic or not? As I said, when you mesh the slab and beam together, these elements are acting together as an integrated structural system, and a slab stiffness will be mobilized when the beam deflects more than the slab, so the slab directly transferring loads to the columns. But we need to see how much that difference will be. The moment definitely is not correct. The deflection, we need to see how we can see that. We need to model a composite beam here.